Hello everyone, this is Doug, and in this video I'm going to start talking about the reductions of carbonyl compounds that use hydride donors. And hydride, right, we're not talking about protons. Protons are H+, and hydride, since it has an "ide" ending, we're talking about H-. So a hydrogen with 2 electrons, it's filled its little duet there. So we're talking about the hydride, negative hydrogen. Those are the things that we're going to add into carbonyls to reduce the carbonyls back to alcohols. So, right, remember, we're talking about carbonyl compounds, so like aldehydes, esters, carboxylic acids, those sorts of things. And remember, we talked about with that general addition reaction, right, if we had some sort of, let's use an R group here. Let's say we have an R group and a carbonyl, and another R group, and we're going to add some sort of nucleophile, right? We're saying that an addition reaction just means that you've added your nucleophile to your compound. And I did mention in the other video that usually what happens is you have some sort of acid or some sort of proton source, because we're going to reduce these down to alcohols, right? So this H ends up going on that O- and getting protonated. Now, and if you want reaction arrows for that, I can give you those, right? Nucleophile attacks there, kicks up. This is just like what we saw in the other video, and then you get your product. And then we have the MO, well, not version, it's supposed to say the same thing, right? These models are supposed to have predictive power for us. And so with the MO version, I think I drew something like this, where I had an R group and another R group and then the carbonyl. And I said, okay, well, we're going to have a nucleophile here. And we're going to have an MO. So here's my pi star. And again, notice that I have the carbon side bigger than the oxygen side. It doesn't matter which side is shaded or unshaded. That's completely arbitrary. But I just picked this. And remember that we said that when my nucleophile here, let me add some electrons on my nucleophile. When my nucleophile attacks, right, it's dumping those electrons into that molecular orbital, which causes the pi bond to break, which is going to give us, if I draw this over here again, so which is going to give us the carbon with the O, an R group, another R group, and now this oxygen has 3 lone pairs, whereas before it only had 2 lone pairs. And now my nucleophile is attached. And we've got a negative charge now on the oxygen, assuming that there's a negative charge on this nucleophile. So that's how the nucleophile attacks, right? It dumps into that pi star, and I should put that too. This is your pi star on your carbonyl, makes it a single bond, and then like I said, in that second step here, I don't have these perfectly lined up, but then your O- just picks up the H+ to give you your product, which would have your nucleophile attached to your carbon, which had whatever groups were there, whether they're R groups or H's, doesn't matter. I'll try to stay consistent though and keep them R groups. And that gives us our alcohols. So what we want to talk about next here, right, is how, or which hydride donors do we have? We have a lot. There's actually a lot of choices. We're just going to look at the first couple of choices on the most really common ones. So our 2 most common ones are sodium borohydride and lithium aluminum hydride, sometimes called lithium aluminum tetrahydride, but it's the same thing. If we look at these reducing agents here, I'm going to draw them out for you so you can see what they look like, right? So it's sodium borohydride. So you got your boron here. It actually has a full octet. It has all those electrons. So you've got a BH4. And if you do your formal charge stuff, you'll see that there is a negative on that boron there. And then we have a sodium and A+ to help balance that charge out. The structure for the lithium aluminum hydride is basically the exact same thing. It's just with aluminum, which is 1 down on the periodic table, right? It's in the same group. Aluminum minus, only we're using lithium now instead. And there are reagents, like there is sodium aluminum hydride and stuff, but you're going to see lithium for sure. Now, something important to notice about these 2 structures, right? They're both going to be hydride donors. They're both things that are going to try to spit out an H-. And what I want you to look at is the polarity of these bonds here. So let me highlight this bond. If I look at this bond right here, I want to know how polar it is or is not. And I want to compare them because that has a lot to do with their different reactivities, right? So if I look at boron, boron has an electronegativity of, let's see, let me get this up for you all. Aha. Boron has an electronegativity of 2.04. Hydrogen has an electronegativity of 2.20. So that difference in electronegativity is really pretty small, right? It's only 0.16. It's almost nonpolar. I mean, you would consider it a nonpolar bond. It's a very, very, very small difference. It's almost, I'll put almost nonpolar. And if we look at the same thing at aluminum and hydrogen over here, obviously hydrogen is going to be the same number, 2.20, but aluminum being lower down is not as electronegative. Aluminum is only 1.61. And that gives us a difference in electronegativity of 0.59, which means it's much more polar. Much more polar, it's much more ionic than the other one is. One's more covalent, one's more ionic. And that becomes important because this, right, this bond right here has more ionic character than the other one. And it's this more ionic character, the fact that there's a larger difference in electronegativities, is going to lead us to use lithium aluminum hydride when we need a stronger reducing agent. So as far as the relative strengths go, lithium aluminum hydride, or LaH, is considered a quote unquote strong reducing agent, whereas sodium borohydride is considered much more weak. It's a weak reducing agent, whereas lithium aluminum hydride is a stronger reducing agent. And again, it's because of that more ionic character. And part of the issue with it being a strong reducing agent means that it's going to be also considered a strong base. It's also going to be considered a strong base because it basically spits out these hydrides like crazy. It spits out these H minuses like crazy. And you'd imagine that those would be a strong base, right? A negative hydrogen, not very stable. It's going to be a very strong base. Whereas the sodium borohydride does not. It's not a strong base. And this has some important implications for the types of solvents that can be used. For sodium borohydride, you can use protic solvents. In fact, you usually see it in protic solvents. So I'll put can use protic solvents. You typically see things like ethanol, methanol being used for sodium borohydride because those protic solvents, there is no acid-base reaction with them. So you don't have to worry about it because it's a strong base. You don't have to worry about there being an acid-base reaction. Now with lithium aluminum hydride, since it is a strong base, you do have to worry about acid bases, right? So you have to, basically you're going to use an ether solvent. You're going to use an ether solvent, and I'll write to avoid unwanted acid-base reactions. Whoops, unwanted. I'm sure there's lots of spelling mistakes in my videos, but I caught this one. To avoid unwanted acid-base reactions. Right? Because it's a strong base, if you add like ethanol or something like that, it's just going to deprotonate your ethanol to make ethoxide. If you add water, it's going to deprotonate water to make hydroxide. If you, heaven forbid, you put an acid in there, it's going to react with your acid immediately, produce H2 gas. Hopefully don't blow yourself up. So you're going to see ethers being used with LaH. So things like diethyl ether or THF. Those are going to be really, really common ones. So another consequence of them being strong and weak is that they only work with certain carbonyls, right? So sodium borohydride is the weaker one, so it only reacts with the most reactive carbonyls. And if you remember in that previous video, we talked about aldehydes versus ketones versus esters versus amides, etc. And if you remember, the most reactive of those functional groups were the aldehydes and ketones. And that's really the only one that sodium borohydride works with. So it only reacts, I'll put only reacts with aldehydes and ketones. Because those were the most reactive carbonyls. I'll even make a note here, right? Because these were the most reactive Those were the most reactive carbonyls. Right? They're the most electron poor. They reacted the most quickly. So sodium borohydride will only work with aldehydes and ketones. You add it to, like, say, an amide or an ester, it's not going to do anything. It's not going to do anything. LiAlH, on the other hand, being a strong one, will react with all carbonyls. So it'll react with all of them. You might have to heat up something to, like, an amide or something like that a little bit, but it's going to react with all of them. So I'll say reacts with all carbonyls. So it will react with esters and amides. We're not going to talk about that in this video, the fact that it reacts with esters and amides also. That will kind of come back to when we talk about the carboxylic acid derivatives. Right now, we're just kind of focusing on aldehydes and ketones. But I do want you to make a note right now that LiAlH reacts with all the carbonyls, not just aldehydes and ketones. And then the last little bit of this here is how many moles of hydride per 1 mole of reagent do you get? Sodium borohydride, basically only good for 1 mole. 1 mole of hydride per mole of sodium borohydride. It's only really good for about 1. So you add it in stoichiometric amounts, 1-to-1 ratios to reduce whatever you want. LiAlH is a little more fiery, and while both of them have 4 hydrogens on them, LiAlH is the only one that's able to donate multiple, and it actually donates a little bit more than 3 moles of hydride per mole of LiAlH. And I don't remember with the paper where they discuss how I think it's like 3.2 moles equivalent or something like that. Per, so it doesn't give up all 4, but it's somewhere between 3 and 4 that it gives up if you dump in a whole bunch. So LiAlH can be used not only to reduce less reactive carbonyls, but it can contribute many hydrides to reduce many carbonyls, or reduce them more than once, which again we'll see kind of in the future. And so really the only difference between these two is what that central atom is, either boron or aluminum. And the difference there is just that they have different electronegativities, so you get either a more ionic character, which is more reactive, or you get more covalent character or nonpolar character, which is less reactive. So let's take a look at these mechanisms and some practice. So let's take a look at the mechanism of how these two reagents work, of these hydride donors. I'm going to make a little, well, let me draw an example right here, and then I'm going to make a little note, and I'm going to come back to it. So here's, say, my 2 butanone, and I'm going to have NaBH4, ETOH. This is how you'll classically see sodium borohydride written out, whether it's in the Journal of Organic Chemistry or an ACS exam or my practice stuff. The sodium borohydride's on top, usually the solvent's on the bottom. Ethanol is a really common solvent for this stuff. It's not a two-stepper, right? It's all together. I don't have 1 and 2 written down. But before I draw the mechanisms, I want to make a note over here on the side of how you want to think about these things being hydride donors, right? So let me put my BH4 over here, minus, right? And there's a sodium hanging around somewhere. The idea is that these are hydride donors because, yes, boron wants to have 4 bonds, so it has a full octet, right? Full octets are really important. But the downside is that it's negative when it has that, right? There's a negative on that boron. The formal charge is a -1. And it does not particularly want to be negative. It's not exactly the most electronegative element in the world. And so what you get, you can kind of think about this as being an equilibrium where it spits out a hydrogen and makes BH3, which is neutral, and a hydride. So now the hydrogen is negative. And if you remember from that previous video, or not previous video, but the previous page, we said boron had an electronegativity of 2.04, whereas hydride has an electronegativity of 2.20. So hydrogen is actually more electronegative than boron is, and so is a little bit better at holding a negative charge than boron is. So as far as the electronics go, it's more favored to the hydride side. Like I said, you kind of lose the octet, which makes it not great. And so you have kind of this equilibrium. You can think about it as having an equilibrium where the H leaves as a hydride, pops back onto the boron to become the borotetrahydride, and then back and forth and back and forth. So as far as mechanisms go, for me, I don't care if you show me the hydride itself attacking the carbonyl, or if you show me the BH4 thing attacking the carbonyl. Let me show you what I mean by that. So let me draw over here by my 2 butanones. So boron, draw my 4 hydrogens, right? Minus, there's a sodium floating around somewhere. What I'm saying is that I don't mind when you draw this mechanism if you have, what you're going to see in most textbooks is this bond breaking, but not that the electrons are going onto the H to make the free hydride, because that's so high in energy, but instead to have it go directly to that carbonyl we were talking about. And I should have put this before, but remember when we were talking about the general mechanism earlier? You attack that because there's a partial negative on oxygen and partial positive on that carbon, right? It has that big old empty pi star. It's a positive charge of that carbon. So your hydride, your H minus, is attracted to the positive thing. But, right, that carbon can't have 5 bonds. It can't have 2 bonds to carbons, a double bond to an O, and a bond to an H. So something's got to give. The weakest bond on here is the pi bond, so we kick up those electrons. That's all one step. And what you're going to notice here is that I'm not going to draw, you've probably seen me draw a lot of reversible arrows. This is not a reversible arrow. Because when I draw this, right, so O, now we've got all these electrons on here, and now there's an H. Now we have an H, and then you have your BH3 and your Na+. The idea here is now, these electrons are not going to drop down and kick out the hydride again, because the CH bond is so strong. It's not going to kick them out. H is not a good leaving group. We don't have any good leaving groups on here, so that O minus is just going to stay. But my product is going to be an alcohol, so the question becomes, well, where do I get that H from? And the answer is from the solvent. So usually these sodium borohydride reactions are done in a protic solvent, an alcohol, for example. And so you're just going to get your ethanol. I'll draw ethanol here. You're just going to protonate that alcohol that you made, or you're going to protonate that alkoxide that you made with the alcohol from your reaction mixture, just your solvent. And that is going to give you your product. Now I'm going to draw in the H just to emphasize it, right? Because that was the H that was added here, this sucker. I'll do it like this, right? This H is that H is that H. But of course, we don't often draw, we don't often draw CHs, right? So you're totally fine with me, and you're just going to see answers being written out like this, where it's just drawn without the H being shown there. So you went from the 2-butanone to the 2-butanol. So you reduced it from having 2 bonds to O to just 1 bond to O. And it looks like that's all you did, but really you added another hydrogen, right? You added that green hydrogen. Now the mechanism for the lithium aluminum hydride is really, really similar. The only difference is that we have to change solvents, and instead of having one step, we have to have 2 steps. So I'm going to use the same starting material just to emphasize the similarity. So step 1, we're going to use lithium aluminum tetrahydride. I'm going to put slash so I can put a solvent on here. And again, the most common ones you're going to see are THF, which is tetrahydrofuran, or diethyl ether. I'll do THF. And let me draw it out here. That's tetrahydrofuran. That's this sucker, right? It's just a cyclic ether. And then step 2 is going to be some sort of acid workup step, right? There's some sort of acid workup. Because you just need to protonate the O minus. So the O minus that we had up there, it's the same deal. I'll draw a line here. It's the same deal as up above where you have an O minus. It's just in this case, since we have nothing protic in step 1, we need to add something protic in step 2. And so this acid, I'll make a note right here. This acid, right? This acid could be anything from like a little bit of HCl. It could be something much weaker like sodium bisulfate. It could be ammonium chloride. It could be something as weak as water. It could even be water. Water is used as a workup step. Anything that could possibly give an H plus so you can get your product. That's all you're looking for in step 2. So the mechanism, same deal. I've got my aluminum. I've got my hydrogens. That H got away from me. and that's negative. And we're going to have the same thing, right? That carbonyl is negative, that carbon is positive. The oxygen's negative, the carbon is positive. So you're going to see the same thing, where I'm going to have the H go and attack the carbonyl. Those electrons kick up. Again, it's a one-step reaction, or sorry, it's a one-way reaction. So now that oxygen's negative, we just added a hydride, and you have aluminum H3, and then plus some lithium hanging out somewhere. Now this is where, so this is all the stuff that happened in step 1. This is where it stops at step 1. The oxygen probably adds into the aluminum and stuff. We don't really need to worry about that, but you're stuck here at the alkoxide. This is where your step 2 stuff comes into play, right? This is where that acid workup comes into play. So let's just say I used, for example, the sodium bisulfate, right? So I'll do O, S, double bond O, double bond O, O minus. So let's say I use that one. Doesn't really matter which one, you just need to have a proton source so that you get your product. Which again would be the exact same product as before. So both of these reagents are going to be really similar in their mechanisms and really similar in the products that they yield. It's just their big differences in their reactivity. So let's take a look at that. Here's a bunch of examples. I'm going to do the first 2 and then maybe suggest that you take a crack at them yourselves here. So I've got sodium borohydride, which I should make a mental note, right, is the weaker one. This is my weaker of the 2, which means I can only use it on aldehydes and ketones. This sucker's a ketone, which means I'm going to be good to go, right? This is going to be a ketone. I like drawing like little mini mechanisms for myself, so I'm just going to draw a hydride. It came from the borohydride, but I'm just going to draw a hydride and have this attack there, and that kicks up so that I can kind of mentally see that this product here I should still have the cyclohexane piece. And then I'm going to have an O, what would be an O minus, but I know that I'm going to add that H on at the end, so it's just an OH, right? Where I didn't draw it, but technically I added this little H here, right? I added that H there. The blue one is the one that came from my borohydride. The red one, say this red one right here, the red one is this one up here, right? The one that came from protonating it. So I would just let me draw that out again so that it doesn't look so funky. I just changed my ketone to an alcohol. That's all we did. I'm going to go to the second one, take a look at that. Again, I'm using the weaker of the 2 agents for this, the sodium borohydride. And over here, I have an amide. And now this is where I should remember, oh, wait a minute, those don't work on amides or esters or anything, right? They just stop, just no reaction, not going to happen, not going to work. So this would be a good place for you to pause, take a crack at the last 4, keeping those things in mind. All you're going to do is add 1 hydride to any carbonyl that reagent can react with. So go ahead and pause, take a crack at these 4. Well, I get a drink of water. Okay, so step 1 of this is the lithium aluminum hydride, and here I have the diethyl ether. So, right, that just looks like this. But this one, right, is the stronger of the 2. This is the strong one, which means it can reduce any carbonyl, which seems to be fine, no big deal. This is a ketone. Those are relatively easy to reduce, but certainly I could use that. And here my step 2 is just some generic H+, just some generic acid. That's totally fine. You could see H+, again, you could see something generic like H3O+. Just some sort of generic proton source is all we're looking for. So I'm going to do the same thing for this one. I'm just going to take my carbonyl. I'm going to turn it into an alcohol. I've reduced it down to an alcohol. And I did not draw the H that added there, but again, that H added at that carbonyl carbon. Here we have the same thing. We have same starting material, but the weaker one, the sodium borohydride, but really no difference. It doesn't matter if you use the strong one or the weak one. They're going to get you the same product. If they're going to react, they're going to get you the same thing. Then I've got the sodium borohydride again, which is our weak one. which, I want to keep in mind it only donates one hydrogen and only works with certain functional groups. So over here I have 2 carbonyls, one aldehyde and one ester. And again, the borohydride only works with the really reactive ones, so aldehydes and ketones. So that means my product is only going to show a reduction at the aldehyde, but not the ester. So my ester, I'm just going to leave alone. But where my carbonyl was over on the other side, turn it into an OH. So that should be my product. So now there's 2 H's at that alcohol carbon. There's the H that was there before plus a new H. And then lastly, I have LAH. Put it with THF this time and water this time. That works fine. The only carbonyl we have is a ketone. It's not going to mess with an aldehyde. It's not going to mess with an alkene. It's not going to mess with the aromatic ring. So I just keep all of this stuff intact and reduce my ketone. That's how you reduce carbonyls with hydride donors, sodium borohydride and lithium aluminum tetrahydride. We will introduce other ones later like diabol, but right now those are the only hydride donors that we're going to deal with. So practice up, happy studying, good luck.